In question 1, we've got a small stone projected vertically upwards with a speed of 20 meters per second from a point O, which is 5 meters above horizontal ground, and we need to find the speed of the stone at the instant when it is 2 meters above the ground. Well, let's start by drawing a diagram showing the situation. So the launching point is 5 meters above ground. We are trying to find the speed when we are 2 meters above ground. So when we are exactly 2 meters above ground, which means 3 meters below the launching point, we know that the u, the initial speed, is 20 meters per second. We've got the acceleration to be minus 9.8 meters per square second because gravity is fighting motion, and we've got the displacement to be negative 3 meters because we are 3 meters below the launching point. I will be using v squared is equal to u squared plus 2as, which means that we've got v squared is equal to 20 squared plus 2 times minus 9.8 times negative 3. So we get v squared to be 458.8. If I take the square root, we get that v is 21.4 meters per second. Remember that because we're using g to be 9.8, we should be quoting final answers to 2 or 3 significant figures. In part B, we need to work out the total time between the instant when the stone is projected from O and the instant when it first strikes the ground. So for this part, I will be using S is equal to ut plus a half at squared. When we hit the ground, we have that the displacement is negative 5 because we are 5 meters below the launching point. So negative 5 is 20t plus a half times the negative 9.8 t squared. This leads to negative 5 being equal to 20t minus 4.9 t squared. I will collect everything on the left hand side to get 4.9 t squared minus 20t negative 5 is equal to 0. And I will be using the quadratic formula to determine the values of t. So t is negative minus 20 plus minus the minus 20 squared minus 4ac and all square root and all divided by 2a, which is 2 times the 4.9. Well, plugging this on the calculator, we get an answer for t which is 4.32, or alternatively t is negative 0.236. Well, t is time, so a negative value for t is not possible, so we reject this. We say it's not valid, and therefore we conclude that the time needed is 4.32 seconds. In question 2, we've got two particles P and Q having masses of 2m and m respectively. They are moving towards each other in opposite directions when they collide. Now, before the collision, P was moving with a speed of 3u and Q with a speed of 2u, and the magnitude of the impulse exerted on Q by P is 5mu, and we need to determine the speed of P immediately after the collision. Well, the first thing to do is draw a diagram. We've got the two particles with the corresponding masses. Now, before colliding, they were moving towards each other with speeds of 3u and 2u respectively. And after the collision, we will assume that they are both moving to the right with speeds of vp and vq respectively. And we will let the mathematics determine whether the assumption that they are both moving to the right is indeed correct. Well, let's recall that the impulse is the change in momentum. It's mv minus mu. So if we consider P was moving to the right, the impulse is acting to the left because it collides with Q, and therefore we can say that the impulse on Pi is equal to mv, so the mass is 2m, and the velocity after is vp minus 2m times the 3u. Well, the impulse had a magnitude of 5mu, so the impulse itself is negative 5mu, which is equal to 2mvp minus 6mu. So we get that mu is equal to 2mvp. We can see that the m's cancel out, and therefore we get that a half u is equal to vp, and therefore we conclude that the speed of p after the collision is a half u meters per second. In part B, we need to determine the speed of q immediately after the collision, so I will be using the conservation of linear momentum here. So the momentum before the collision is simply 2m times 3u plus the m times the negative 2u, because the particle q is moving to the left, is equal to 2m vp plus m times vq. So we get that 6mu minus 2mu is equal to 2m times the vp, which was found to be u over 2, plus mvq. So we get that 4mu is equal to mu plus mvq. So we have 3mu is equal to mvq. Again, the m will cancel out, and we get that the velocity of q is 3u, and therefore we conclude that we're looking at a speed of 3u meters per second. In question 3, we've got a parcel of mass 20 kilograms at rest on rough horizontal floor with the coefficient of friction being 0.3. We've got two forces acting here, the 200 newtons at 15 degrees above the horizontal and to the left, and the t newtons towards the right at 25 degrees above the horizontal. We're being asked to find the smallest value of t for which p remains in equilibrium, and the first thing to do is add the forces. Well, obviously we've got the weight of 20g, and then I will take the 200 newtons and resolve it into the horizontal and vertical component, which is 200 cos 15 and 200 sine 15 respectively. Similarly, I'll do the same for t newtons here, which is t cos 25 to the right and t sine 25 upwards. Obviously, there is a reaction force here acting upwards, and since we are told to find the smallest value of t for which p remains in equilibrium, if t is as small as possible, then the parcel p is about to go to the left, and therefore we've got friction acting to the right, and actually this friction is attaining its maximum value. I will now consider balancing the forces acting upwards and downwards. So we've got that 200 sine 15 plus the reaction force R plus t sine 25. This must be equal to 20g, because the forces acting upwards is equal to the forces acting downwards. And this means that the reaction force R is equal to 20g minus 200 sine 15 minus the t sine 25. We also have that the frictional force F is equal to the maximum frictional force F max, which is mu R. Well, in our case, the mu is 0.3, so F is 0.3 R. I will then consider the horizontal forces. So forces acting to the right must be equal to the forces acting to the left, and this leads to T cos 25 plus the frictional force F is equal to 200 cos 15. Remember, we're trying to determine T here. Well, I will be replacing F with the 0.3 R. So we've got T cos 25 plus 0.3 R is equal to 200 cos 15. And then I can proceed in replacing R here with the expression we obtained above. And therefore we get T cos 25 plus 0.3 times the 20g minus 200 sine 15 minus the t sine 25 is equal to 200 cos 15. So this is an equation that only involves t. I will expand to get t cos 25 plus 6g minus 60 sine 15 minus 0.3 t sine 25 is equal to 200 cos 15. Well, I will leave the terms containing t on the left hand side, and I will factor out the t. So we get t brackets cos 25 minus 0.3 sine 25 is equal to 200 cos 15 minus the 6g plus the 60 sine 15, which means that t can be found by doing 200 cos 15 minus the 6g plus the 60 sine 15, and all of it divided by the cos of 25 minus the 0.3 sine 25. We'll plug everything on the calculator. Be careful here because we are using G to be 9.8. Then I need to code my answer to 2 or 3 significant figures, where we get that T is 192 newtons. In question 4, we've got the metal rod AB with a weight of W newtons and length of 6 meters. This is a situation here when a force of magnitude 900 newtons is applied vertically upwards at A, then the girder is about to tilt about D. We need to determine the value of X, and we are modeling this as a non-uniform rod with a center of mass that is found at a distance of X meters from A. Well, the first thing to do is put the forces and the distances on the diagram. So we've got the weight of W, we've got the 900 newtons acting at A vertically upwards, we've got the reactions at C and D, and the distances, well, the weight is X meters from A, and this means that the distance between the center of the mass and D is simply the 6 minus the 1 minus the X, so it's simply 5 minus X. So because we are about to tilt about D, this means that we have no reaction at C, so this is crossed out, and I can proceed by taking moments about D. So if I take moments about D, we can see that the 900 newtons is acting in a clockwise fashion at a distance of 5 meters. So we've got that 5 times 900 is equal to the anti-clockwise moments, which are the W acting at a distance of 5 minus X. So we've got 5 minus X times W. This leads to 4,500 is equal to 5 minus X in brackets times W. We are then told that a force of magnitude 1500 newtons is applied at B acting vertically upwards, and this time the girder is about to tilt about C. So let me add the forces in a second diagram. We've got the weight W, we've got the 1500 newtons acting vertically upwards at B, we've got the reactions at C and D. We know that W is at the distance of X from A, which makes the distance of W from C simply X minus the 1 meter there. Well, if we are about to tilt about C, this simply means that we have no reaction at D. So we can take moments about C, which means that the anti-clockwise moment is the 1500 newtons, which is acting at a distance of 5 meters. So we've got 5 times 1500 is equal to the clockwise moments, which is X minus 1 times W. This leads to 7,500 being equal to X minus 1 times the W. Now recall that we have already established another relationship between X and W here, so I can write one below the other. So 4,500 is equal to 5 minus X times the W. Now I can divide each of the sides, and we've got that the W cancel out, and therefore this leads to 5 over 3 is equal to X minus 1 over 5 minus X. I will proceed by cross multiplying to get 5 times 5 minus X is equal to 3 times X minus 1. So 25 minus 5X is equal to 3X minus 3, which leads to 28 being equal to 8X, and therefore we get that X is 3.5 meters. In question 5, we're dealing with two forces. We've got force F having a magnitude of 8 newtons acting in a direction with a bearing of 240 degrees, and then the force G with a magnitude of 10 newtons acting due south. Now we need to find the magnitude of R, which is the resultant, the sum of F and G. So to do that, I will start by drawing the two forces. So for the force F, we've got the north. If I turn clockwise through 240 degrees at a distance of 8 newtons, that's the force acting. Now we know that the angle with the horizontal here must be 270 minus 240, which gives me an answer of 30. So what I'll be doing, I'll be resolving the 8 newtons acting at a bearing of 240 degrees. The horizontal component will obviously be 8 cos 30, and the vertical downward component will be 8 sine 30. This means that the force F can be written in column form as minus 8 cos 30 minus 8 sine 30. The negatives indicate movement to the left and downwards. This simplifies to minus 4 root 3 and negative 4. Whereas for the force G, the situation is a lot simpler. We just have 10 newtons acting downwards, and therefore we simply have that G is 0, negative 10, and therefore we can proceed in order to find R and then find its magnitude. So R is simply the F, which is minus 4 root 3 minus 4, plus the G, which is 0, negative 10. This gives an answer of minus 4 root 3 minus 14. And I can proceed in finding the magnitude of R. I will simply be using Pythagoras here. So it's going to be minus 4 root 3 squared plus the negative 14 squared and all square root. Plug this on the calculator, we get 2 root 61 newtons for the magnitude of R. We're then asked to determine the direction of R, giving our answer as a bearing to the nearest degree. So I will start by drawing the north, and the direction of R is to the left and downwards, so a diagonal pointing to the left and down. We know that the component to the left is 4 root 3 and the component to the right is 14. So we're trying to determine the angle theta here that will be used in finding the bearing of the force. So we can see that we can close the triangle. The 4 root 3 here comes from the 4 root 3, the component to the left. And therefore we can simply say that tan theta is equal to 4 root 3 over 14. And therefore theta will be found by doing shift tan of 4 root 3 over 14. This gives an answer of 26.3295 ... Remember, we're trying to find the bearing, so from the north, turning clockwise until we look at the direction of the force. So we need to add 180 to theta. So we conclude that the bearing will be found by doing 180 plus the 26.3295 ... Remember, we were asked to give our answer to the nearest degree, so the answer should be 206 degrees. In question 6, we've got Agatha time t0 at the point 11i plus 11j meters and Brioni at the point with position vector 7i plus 16j meters. Now, Agatha skates with a constant velocity of 3i minus j meters per second, whereas Brioni is skating at a velocity of 4i minus 2j meters per second. Notice that they are both skating with constant velocities. There is no acceleration here, and we're asked to find the position vector of Agatha at time t seconds. Well, we know that the position vector of Agatha will be given by the initial position vector plus the speed, the velocity with which we are moving times t. So in our case, it's going to be the 11i plus 11j, the initial position vector, plus the 3i minus j times t, which can be written as 11 plus 3t, that's the I component, plus 11 minus t, and that's the j components, and that's in meters. Now at time t is 6 seconds, Agatha passes through the point P, and we need to show that Brioni will also pass through P, and we need to find the value of t when this occurs. So let me start by using the fact that we can find the position of Agatha when t is 6. So when t is 6, the position vector of Agatha Ra will be given by 11 plus 3 times 6. So I'm replacing t with 6 in the expression we just obtained in part A, plus 11 minus 6, and that's the j component, which gives 29i plus 5j. This is the position vector of point P. We need to show that Brioni will also pass through this point. Well, if RB is the position vector of Brioni, this is going to be the initial position vector, the 7i plus 16j, plus her velocity times t, which is 4i minus 2j times t. This can be written as 7 plus 4t as the I component, plus 16 minus 2t as the j component, and we need to show that there is a value for t that will take this vector to be 29i plus 5j. So if this is equal to 29i plus 5j, the only thing that's left to be done is equate the I components and then equate the j components, which means we've got two equations in t. We've got 7 plus 4t is equal to 29, and 16 minus 2t is equal to 5. So we get 4t is equal to 22, which gives t to be 5.5. Whereas here we've got 11 is equal to 2t, so we get 5.5 again. It is crucial that we get the same value for t, which will allow us to conclude that Brioni will indeed pass through the point P, and this will happen when t is 5.5 seconds. Now at time t seconds, Agatha is at the point A and Brioni is at the point B, and we need to show that the vector AB is given by t minus 4I plus 5 minus tj meters. Well, let me start by stating that the vector AB is simply the position vector of Brioni minus the position vector of Agatha. Well, we found both of these, and RB was 7 plus 4ti plus the 16 minus 2tj, and I will be deducting the 11 plus 3ti that we found in part A plus the 11 minus tj. So this means if I look at the I components, I got 7 plus 4t minus 11 minus 3t, and all of this is the I component, plus 16 minus 2t minus 11 plus t, and that's the j component, which simplifies to minus 4 plus ti plus 5 minus tj meters as required. In part D, we are asked to find the distance between the two gears when they are the closest together. So I will start by finding the magnitude of the vector AB. This will give me a function for the distance between the two gears in terms of t, the time. So it's the I component minus 4 plus t squared plus the j component 5 minus t squared and all square root. I will then expand this to get 16 minus 8t plus t squared plus 25 minus 10t plus t squared and all square root, which can be simplified into 2t squared minus 18t plus 41 and all square root. And I need to determine when this will be a minimum. Now to do this, I could consider completing the square. So we've got 2 brackets t squared minus 9t close brackets plus 41 and all square root, and I will be completing the square on t squared minus 9t. So this is giving me 2 brackets t minus 9 over 2 squared minus 9 over 2 squared plus the 41 and all square root, which simplifies to 2, and I've got t minus 9 over 2 squared minus 81 over 4 and close the brackets plus 41 and all square root, which further simplifies into 2 brackets t minus 9 over 2 squared minus 81 over 2 plus 41 and all square root, which gives me 2 brackets t minus 9 over 2 squared plus a half and all square root. So we can easily see that the distance between them will be a half plus something squared. Well, this square can never go negative, so it will be a minimum when this drops dead, when t is 9 over 2, and therefore we conclude that the minimum distance between the two gears, so the minimum magnitude of the vector AB, will be when t is 9 over 2, and it's simply going to be root of a half. So we've got root of a half meters. Question 7, we've got a helicopter hovering at rest above horizontal ground at the point H. A parachutist steps out of the helicopter, immediately falling vertically and freely under gravity from rest for 2.5 seconds. The parachute then opens and causes him to immediately decelerate at a constant rate of 3.9 meters per square second for capital T seconds, where t is less than 6, until his speed is reduced to v meters per second. He then moves with this constant v until he hits the ground. While he's decelerating, he falls a distance of 73.75 meters, and the total time between the instant he leaves the helicopter and the instant he hits the ground is 20 seconds. We need to find the speed of the parachutist the instant when his parachute opens. Well, we know that he fell from rest, so u was 0. He was falling under gravity, so the acceleration was 9.8 meters per square second, and this was happening for a time of 2.5 seconds. So I'll be using v is u plus at, which is 0 plus 9.8 times 2.5, which gives an answer of 24.5 meters per second. In part B, we are asked to sketch a speed-time graph for the motion of the parachutist from the instant when he leaves H to the instant when he hits the ground. So we've got in the vertical axis the speed and in the horizontal the time in seconds. Remember that we were originally falling under gravity, so we were accelerating, then we decelerated, and then we attained a constant speed. So it should look something like this. We had a time of 2.5 seconds for falling under gravity. Then we were decelerating for capital T seconds, so this is 2.5 plus capital T, and the total time was 20. We found in part A that the velocity attained was 24.5 meters per second in those first 2.5 seconds, and we have been given that the velocity with which we were moving for the last part of the journey was capital V. So this is the situation, this is the speed time graph for the motion of the parachutist. In part C, we're asked to find the value of capital T, and to do that, I'll be revisiting my speed time graph here, and I will be adding the additional information I was provided in the question itself. So first of all, we know that the distance covered while decelerating, so the shaded area here is 73.75 meters, and the deceleration during this time, so the gradient of my speed time graph is minus 3.9. So essentially, I've got 2 points here on this straight line. It's the point with coordinates 2.5, 24.5, and the point with coordinates 2.5 plus capital T, V. So I could be using rise over run. So we've got V minus the 24.5 over the 2.5 plus T minus the 2.5 is equal to minus 3.9. So we've got that V minus 24.5 over capital T is negative 3.9, and therefore this leads to V minus 24.5 is negative 3.9 T, and so we have that V is 24.5 minus 3.9 capital T. We also have that this is a trapezium, and we know that the area of a trapezium is given by base 1 plus base 2 over 2 times the height, and in our case the area has been given to be 73.75, which is the distance covered. Base 1 is 24.5, base 2 is capital V over 2 times the height of the trapezium, which is capital T. So we get 147.5. I cross multiplied. I multiplied the 73.75 with the 2 is equal to 24.5, and I will be replacing the V with 24.5 minus 3.9 T, close brackets, times T. So we get that 147.5 is equal to 49 minus 3.9 T times T. I will further expand to get 147.5 is 49 T minus 3.9 T squared. And I could collect everything on the left hand side to get 3.9 T squared minus 49 T plus 147.5 is equal to 0. And I could proceed by using the quadratic formula to determine the values for T. So T is negative minus 49 plus minus the minus 49 squared minus 4AC and all square root and all divided by the 2A. So I will be dividing by 2 times the 3.9. So this gives an answer for T which is 5, or the other answer is T is equal to 7.56. However, remember that in the question we were told that T is less than 6, and therefore I reject since T is less than 6, and therefore we conclude that the time taken was 5 seconds. In part D, we need to find to the nearest meter the height of the point, the H above ground. So we're trying to find the total distance covered. We already know that the distance here in the middle is 73.75 meters. We have found T to be 5, which means that the 2.5 plus T here is 7.5. So I will start by finding V. Well, V is 24.5. We said minus 3.9 T, which was found to be 5. This gives an answer of 5. So we've got this height here to be 5. and therefore we have that the total area will be the triangle here, which has a base of 2.5, a height of 24.5, so I'm doing base times height over 2, plus the 73.75, plus the area of the rectangle at the very end, which has a width of 20 minus 7.5 and a height of v, which is 5. So plug this on the calculator with 166.875 meters, which correct to the nearest meter as instructed is 167 meters. In question 8, we've got two particles A and B having masses of 2 and 4 kilograms respectively. They are connected with a light inextensible string as shown here. The angle at the bottom here, alpha, is satisfying tan alpha is 3/4. We are releasing the system from rest, and with the string taut, B descends. We need to find the tension in the string as B descends. So the first thing to do is obviously add the forces acting here. We've got the weight of B 4G and the tension pointing upwards. We've got the weight of A of 2G, which I will be resolving perpendicular and along the plane. So we've got the vertical component, the perpendicular component to the plane being 2G cos alpha, and the horizontal component, the component along the plane, being 2G sine alpha. And you also have the friction here, because as B goes down, A will move up, and therefore we've got friction opposing motion. We've got the tension as well pointing upwards. We've got the reaction perpendicular to the plane, and since the string is inextensible, both A and B are moving with the same acceleration, A. Now we've been told that tan alpha is 3/4, so we are obviously looking at the 3, 4, 5 triangle, which means that sine alpha is going to be 3/5 opposite over hypotenuse, whereas cos alpha will be adjacent over hypotenuse, which is 4/5. Now considering B first, well, B moves down, so I'll be doing forces acting downwards, 4G minus forces acting upwards, T, is mass of 4 times acceleration of A, whereas if we consider A, then we've got A moving upwards, so we've got that T minus the 2G sine alpha plus the F is equal to mass times acceleration. Remember, it's the same acceleration. So we've got that the reaction here, if we look at the diagram once more, is equal to 2G cos alpha. So we've got that R is equal to 2G cos alpha, and we know that cos alpha is 4/5, so 2G times 4/5, which gives an answer of 15.68 newtons for the reaction R. Well, since we've got motion, the friction attains its maximum value F max given by mu R. We have that mu is 1/4 and the reaction is 15.68, and therefore we've got that the friction is 3.92 newtons, and therefore we can proceed with the 3.92 newtons and substitute it here to get that T minus 2G times sine alpha, which is 3/5, minus the F, which is 3.92, is equal to 2A. This leads to T minus 15.68 is equal to 2A, and we're essentially dealing with simultaneous equations in T and A. So I could multiply this by 2 to get that 2T minus 31.36 is equal to 4A, and since both of these equations are equal to 4A, I can simply equate them. I've got 4G minus T is equal to 2T minus 31.36, which leads to 70.56 being equal to 3T, and therefore we get that T is 23.52. Remember, since we've been using G to be 9.8, we need to give our answer to 2 or 3 significant figures. The 4 significant figures here would be penalized, and therefore we need to say that T is 23.5 newtons. Now on hitting the ground, B immediately comes to rest and A comes to rest before reaching the pulley. We need to find in terms of H the range of possible values of D. So the first thing to do is revisit one of the equations involving t and a. So we had 4g minus t is equal to 4a. So 4 times 9.8 minus the 23.52, which was the exact value for t, is equal to 4a, which leads to 15.68 is equal to 4a, and therefore the acceleration is 3.92 meters per square second. And if we look at our diagram once more, the moment that B hits the ground, it has traveled a distance of h meters. So A has moved up the plane by h meters, so it's somewhere here. And the string goes slack, and then A moves under gravity. We can start by finding the speed of A the moment the string goes slack. So remember, the A was initially at rest, so U was 0. It was moving with an acceleration of 3.92 as we just found above, and it covered the distance of h, so I could be using v squared is u squared plus 2as, so v squared is 0 squared plus 2 times 3.92 times h. We get v squared to be 7.84h, which means that v is 2.8 root h. This is the speed of A the moment the string goes slack. So considering A when string goes slack, A is going up the plane, so I'll be doing forces acting up the plane, which is 0, minus forces acting down the plane, which is the component of the weight 2g sine alpha plus the friction F. This should be equal to 2a. Well, we have already found the 2g sine alpha plus F to be 15.68, so minus 15.68 is equal to 2a, which means the acceleration is negative 7.84. Well, we are not surprised that we get a negative answer, because the moment the string goes slack, it is decelerating, because you only got the weight and the friction opposing motion. So I could use Suvat once more. So I would be modeling the journey the moment the string goes slack. The initial velocity here is what we just found to be the 2.8 root h, and it eventually came to rest, so the final velocity is 0. So let me write this down. We've got u is 2.8 root h, v is 0. The acceleration was found to be minus 7.84, and I could use v squared is u squared plus 2as. So v squared is u squared plus 2as means that 0 squared is 2.8 root h squared plus 2 times the minus 7.84 times the displacement of s. So we get that 0 is 7.84h minus the 15.68s. So 15.68s is 7.84h, which means that s is h over 2. This is the distance covered while the string went slack, and we know that the h that was covered while B was descending, together with the extra distance we just found to be h over 2, has to be less than d, because we know for sure that particle A came to rest before reaching the pulley. This simply means that h plus h over 2 must be less than d, so we get that 3h over 2 is less than d. And finally, we need to state one physical factor other than air resistance that could be taken into account to make the model more realistic. Well, there are several things you could mention here. Someone could say that the pulley is not smooth. We have assumed that there is no friction at the pulley, which is unlikely to be the case. A second thing to mention is that the string is not light. And finally, the string is not inextensible. It's another physical factor that could have been taken into consideration.